Welcome to a review lecture 4.3, resistance resistivity. Upon completing this unit, you should be able to calculate the resistance of components, define the difference between resistance and resistivity, use Ohm's law to define the relationship between potential resistance and current. Now, resistance, the amount of charge that flows in a circuit depends on the voltage provided by the voltage source. The current also depends upon the resistance that the conductor offers to the flow of charge, otherwise known as the electric resistance. This is similar to the rate of water flow in a pipe, which depends upon the pressure difference and the resistance of the pipe. For a given pressure, more water passes through a large pipe than a small one, because a large pipe has a lower resistance. Similarly, for a given voltage, more electric current passes through the large diameter wire than a small diameter wire, because a large diameter wire has lower resistance. There is an analogy to plumbing which we've been making over and over again. A simple hydraulic circuit is analogous to an electric circuit. The fluid flow is the current, the resistance is the resistance, the switch is the valve, the pump is the battery, and the pressure difference across anything is the potential difference. In Ben Franklin's day, electricity was thought to be a weightless, frictionless fluid. Although not strictly correct, because quantum mechanics is very hard to describe, the model is still extremely useful more than 200 years later, close to 300 years later. Okay, resistance and resistivity. If you apply the same potential difference between the ends of geometrically similar rods of copper and glass, you get very different currents. The characteristic of this conductor that enters here is the electrical resistance. The resistance of R of a conductor is R equals V over I, where R is the resistance, V is the voltage, and I is the current. The unit on this is the new unit ohm, the unit of resistance, and that equals volts divided by amps. V is the potential difference across the conductor, I is the current through the conductor. Now, several texts hang on to the delta when discussing potential difference. However, since practically no one else in the world does this, I'm going to drop the delta. When we talk about gravitational potential energy, we recognize that we are concerned with differences in potential energy. It's the same situation. Instead of the resistance R of an object, we may deal with resistivity rho of the material. Rho equals E over J, and the units on rho are ohm meters, where E is the electric field strength in volts per meter, and J is the current density in amps per meter squared. The reciprocal resistivity is the conductivity sigma of the material. Sigma equals 1 over rho. Note on units, we use the Greek letter omega for ohms to avoid confusion between the letter O and the number 0. If you write something like this, unless you're really careful about this, it'd be very confusing. Okay, the resistance R of a conducting wire of length L and uniform cross-section is R equals rho L over A. A here is the cross-sectional area. And of course, the resistivity rho for most materials actually changes with temperature. For many materials, including metals, the relationship between rho and the temperature T is approximately linear over moderate temperature ranges. It is approximated by the equation rho minus rho naught equals rho naught alpha times T minus T naught. T naught is the reference temperature, rho naught is the resistivity at T naught, alpha is the temperature coefficient of the resistivity for the material. Okay, so each material has its own resistivity. It's a characteristic of the material. The resistivity of metals increases with temperature, so alpha is greater than 0. And basically, it looks like this for metals. Thermal agitation of the many free electrons interferes with the movement of charge. The resistivity of semiconductors decreases with temperature, so alpha is less than 0. Thermal agitation frees up more electrons to conduct charge, so they're sort of the opposite. Non-conductors have extremely high resistivities and resistance. There are no free electrons to conduct charge unless the potential is so high that the material breaks down and conducts. Here's a table of resistivity and temperature coefficients of resistivity for various materials at 20 degrees C. This 20 degrees C, by the way, is T naught. The resistivity is rho naught. This temperature coefficient of resistivity is the alpha. I want you to just notice some things here. The resistivity varies from, for silver, which is an extremely good conductor, from 1.59 times 10 to the minus 8th, to quartz, which is an extremely good insulator, which has a resistivity of 73 times 10 to the 16th ohm meters. That is a factor of 4.7 times 10 to the 25th times difference in resistivity between those materials. The temperature coefficient of resistivity for the metals is positive. That means the resistivity goes up as the temperature goes up for metals. The temperature coefficient of resistivity for semiconductors is negative. That means the resistivity goes down as the temperature goes up for semiconductors. Okay, what factors affect the resistance of a wire? The resistance of a wire depends on the material used in the wire, that is its resistivity, also on the thickness and the length of the wire. The resistivity is also dependent on the temperature. An example, a rectangular block of iron has dimensions 1.2 by 1.2 by 15 centimeters. A potential difference is to be applied to the block between the parallel sides, and in such a way as those sides are equal potential surfaces. What is the resistance of the block of the two parallel sides or the square ends with the dimensions 1.2 by 1.2 centimeters, or the two rectangular sides which dimensions 1.2 15 centimeters? Now, I would expect, knowing that R L over A, I would expect the area, the part that has the greatest area, that's going to have the lowest resistance. So 2 is going to have a much lower resistance than 1. The physics of this is a resistivity problem. We write down the knowns and unknowns, convert them to SI. L is the long dimension, that's 0.15 meters. H, or D, and D are the two square dimensions, that is 0.012 meters. Rho is for iron, look it up, 9.68 10 to the minus eighth ohm meters for iron, and we need to know R. Okay, so R equals rho L over A, and the area is X times Y, it's square. So the resistance is rho L over A, and R1 is rho L over H times D, and R2 is rho L over HL, rho over L. So here's the 1.2 by 1.2 side. So R1 is rho L over H times D. So here's our resistivity of 9.68 times 10 to the minus eighth ohm meters. Here's our L dimension, 0.15 meters, and of course the H times D is just 0.012 meters squared. Okay, so then R1 equals 1.0 times 10 to the minus fourth ohms. Here is the 1.2 by 15 centimeters, that's the rectangular side. R2 is just rho over L, so R2 is the rho of 9.68 times 10 to the minus 8 ohm meters divided by the 0.15 meters. R2 is 6.5 times 10 to the minus 7th ohms, and it's considerably less than the square side. So the orientation with the largest cross-sectional area had the smallest resistance as expected. Resistance proportional to L over A. The resistance depends upon the geometry, the length, the area, and the resistivity. The resistivity is a property of the material, so it depends on the material and the temperature. Now, Ohm's law. Electric resistance is measured in units called ohms. George Simon Ohm, a German physicist, tested wires and circuits to see what effect the resistance of the wire had on the circuit, had on the current. The relationship among voltage, current, and resistance is called Ohm's law, and I is proportional to V, or I equals V over R. Ohm's law says the current through a device is directly proportional to the potential difference applied across the device. A conductor obeys Ohm's law when the device's resistance is independent of the magnitude and polarity of the applied potential difference. A conducting material obeys Ohm's law when the resistivity of the material is independent of the direction and magnitude of the applied electric field. Such a material or device is called an ohmic device or material. Memory chip for Ohm's law, VIR, V equals IR. Okay, so we have two graphs here. One has a linear response here, and the other one has this. In figure A, a potential difference V is applied across this device that's being tested. The resulting current I through the device is measured as V is varied in both magnitude and polarity. Figure B is a plot of I versus V for one device. This plot is a straight line passing through the origin. The ratio I over V, which is the slope of this line, is the same for all values of V, so it's got a constant slope. This means that the resistance R, which equals V over I of the device, is independent of the magnitude and the polarity of the applied potential difference. So in other words, it works the same even when it's less than 0. This is an ohmic device. Figure C is a plot for a semiconducting p-n junction diode. This would be made out of a semiconductor. Current can exist in this device only when the polarity of the potential is positive and the applied potential difference is more than about 1.5 volts. When the current does exist, the relationship between I and V is not linear. It depends upon the value of the applied potential difference V. This is a non-ohmic device. Now, a resistor is a device whose purpose is to provide resistance in a circuit. The resistance of a resistor is R equals rho L over A. The resistance depends upon the geometry and the material. Most resistors are made to obey Ohm's law and provide a constant resistance that does not vary much over a wide range of temperatures or applied potential difference. Now, some, like this one, are made to be variable. This has a knob that you can turn to vary the resistance. And these are called potentiometers, otherwise known as pots. The circuit symbol for resistance is a zigzag line, and these are all different types of resistors. Now, you may have seen something like this if you got to look inside of some sort of electronic component. This is a resistor color code. I threw this in here just in case Somebody was curious. If you look at a resistor, it typically looks like a little cylinder with two wires sticking out of the end. You'll see these bands of color. First digit is this one, second digit is this one, then there's a multiply, then there's a tolerance. Now this one's always close to one of the wires. The first digit is always close to one of the wires. Okay, so black equals 0 goes this way. The black equals 0, brown equals 1, red, orange, etc. goes to the rainbow. And then white equals 9. Silver is a 10% tolerance. That means plus or minus 10%. Gold is plus or minus 5%. Now, as you look at this resistor, it has red for the first digit, that's a 2. The second digit is a 5 because it's green. The third digit, which is the multiplier, is orange, which is a 3. So this is a 25 kilo ohm resistor, and the tolerance is plus or minus 10%. If you are a Physics 222 student that is calculus-based, please stay right here. If you are an algebra-based physics student, that is Physics 122, please skip ahead 2 slides to number 19. So this is what's going on inside the resistor. The assumption that the conduction electrons in a metal are free to move like the molecules in a gas leads to an expression for the resistivity of the metal, rho equals m over E squared n tau. N is, of course, the number of free electrons per unit volume, and tau is the mean time between the collisions of electrons with the atoms of the material. M, of course, is the mass. E is the charge on the electron. Metals obey Ohm's law because they had the mean free time tau is approximately independent of the magnitude E of any electric field applied to the metal. Now these gray lines show an electron moving from A to B, making 6 collisions. The green lines show what the electron's path would have been from A to B prime, might be in the presence of an applied electric field, E. Notice that the steady drift in the direction of minus E, so electrons swim upstream. And tau is the mean time between these collisions, otherwise known as mean free time. Okay, the acceleration of electron due to Newton's second law is A equals F over m, and that equals E times big E over m, the charge times the electric field over m. The drift speed with average time tau in collisions, Vd equals A tau, that's the acceleration times tau, and that is E times big E tau over m. We're going to combine this with the current density. Vd is J over Ne, and that equals little e times big E tau over m, where J is the current density. That would be terms of amps per square meter. Simplify and solve in terms of field strength. E, which is the electric field strength, is m divided by E squared n tau times J. Compare this with the resistivity. E equals rho J, and we find out that rho equals m over E squared n tau. M, n, and E are constants. And since Vd is much less than the thermal speed, very much less than the thermal speed, tau is also independent of the electric field, which is another way of stating Ohm's law. What does Ohm's law state? Ohm's law states that the current in a circuit is directly proportional to the voltage impressed across the circuit and is inversely proportional to the resistance of the circuit. We use digital voltmeters called DVMs to measure potential and current in labs. You can also use them for resistance. These devices had to be connected properly and set up properly to work correctly and safely. For your safety in lab, let the instructor do this. If you have any questions, stop and ask for help. Now, to measure voltage or potential, that is V equals volts, the digital voltmeter is connected across and in parallel with the element to be measured. So, suppose you wish to measure the potential drop across this resistor in this circuit. You set your DVM to read voltage by turning the dial and to read the proper scale. And then you connect your DVM in parallel with the resistance you wish to remember. And this, by the way, this V in the circle says that you're measuring potential or voltage. To measure current, which is amperage, the digital voltmeter is connected in series with the part of the circuit to be measured. So here, what you have to do is break the circuit and replace one of the wires with this. You also have to set up the dial to measure current and the proper scale. And by the way, measuring current is indicated by this little circle with the A in it. The A stands for amps. So when you see this circle with an A, that means you have a digital voltmeter connected up to measure amperage. If you see the circle with a V, that means you have a digital voltmeter connected up to measure potential or voltage. What is the resistance of a 110 volt toaster that produces a current of 3.1 amps? Okay, the knowns and unknowns. V equals 110 volts. The current is 3.1 amps. What is the resistance? And this should be a small, I don't know why this keeps doing this. Okay, the physics of this is Ohm's law. A toaster has a heating element, which is a pure resistance. So it's okay to use Ohm's law, even for AC. The resistance is V over I. And then it's 110 volts divided by 3.1 amps, that's 35 ohms. How much would you have to raise the temperature of a copper wire, originally 20 degrees C, to increase its resistance 20%. So the knowns and unknowns of copper, T naught is 20 degrees C. We're going to increase the resistance 20%. What's the final temperature? The physics of this is a resistivity problem. You look up alpha for copper. It's 0.0068 per degree C. The formula is rho minus rho naught equals rho naught times alpha times the quantity T minus T naught, where resistance R is rho L over A. We can combine and solve this. The wire has a constant L and A and is homogeneous and isotropic, which means that we can derive the alternate form for resistance versus temperature. R minus R naught equals R naught times alpha times the quantity T minus T naught, or delta R equals R naught alpha delta T. Delta T then is delta R over R naught divided by alpha. In this case, then the answer is 0.20. That's delta R over R naught for the 20% increase, divided by the alpha of 0.0068 per degree C. That is a temperature change of 29 degrees C. The final temperature would then be the 29 degrees C plus the 20 degrees C and would equal 49 degrees C. Now, in this kind of problem, people make this mistake all the time. When they ask you for the final temperature, don't forget this is a change. So you had to add the 20 degrees C to get the final temperature. Okay, a length of aluminum wire is connected to a precision 10-volt power supply and a current of 0.4212 amps is measured at 20 degrees C. The wire is placed in a new environment with an unknown temperature. The new current is now 0.3618 amps. What is the temperature? Okay, knowns and unknowns. It's aluminum. Its initial voltage is 10.00 volts. The initial current is 0.4212 amps. The original temperature is 20 degrees C. The new current is 0.3618 amps, and the alpha for aluminum, you look this up, 0.00429 per degree C. What's the new temperature? The physics of this is a resistivity problem. From the previous example, we can use R minus R naught equals R naught times alpha times T minus T naught, and R equals V over I. We can combine this. We can say that R equals R naught times the quantity 1 plus alpha delta T, and that is equal V over I. And that equals V over I naught times the quantity 1 plus alpha delta T. T equals T naught plus the quantity I naught over I minus 1 divided by alpha. This equals 20 degrees C plus the quantity 0.4212 amps divided by 0.3618 amps minus 1 divided by alpha of 0.00429 per degree C. The answer to this is 58.3 degrees C. This is a way of making very accurate temperature measurements, especially those in extreme environments. For which combination for the length L and radius R of the wire will the resistance have the smallest value and which would have the highest? Well, you want to look at R equals rho L over A, and you don't need to know rho. All you're doing is comparing it. So this is proportional to L over R squared because the area is going to be pi R squared. The pi and the rho we don't care about. List them and put them in a table. So here we did this. We listed the length and the radius, made sure they're all in the correct units, meters. And then we listed the values of L over R squared, and those will be in inverse meters. When we do that, we find that the L equals 0.25, R equals 0.08 has the lowest, and the L equals 0.40, R equals 0.02 has the highest. Okay, a wire resistance R is stretched uniformly, keeping its volume constant until it is twice its original length. What happens to the resistance? Okay, so what's going to happen is going to increase by a factor of 4. If you keep the volume, which is the area times the length constant, if the length is doubled, the area is halved. Since R equals rho L over A, this increases the resistance by a factor of 4. All of the electric devices are required to have identifying plates that specify their electrical characteristics. The plate on a certain steam iron states that the iron carries a current of 6 amps when connected to a source of 120 volts. What is the resistance of the steam iron? The units below are all in ohms. The answer to that is 20 ohms. R equals V over I, or 120 volts divided by 6 amps equals 20 ohms. Suppose an electrical wire is replaced with one having every linear dimension double, so the length and the radius have twice the original value. What happens now? The answer to that is 2, less resistance. Resistance equals rho L over A, which is proportional to L over R squared. If you double L and R, then it'll be 2 over 2 squared, which would equal 1/2. Resistance would be 1/2 of what it was before. Okay, wires A and B are identical except that each is made from a different material. The one end of wire A is connected to one end of wire B. The two remaining ends are connected across the battery and current flows through the two wires. Which one of the following statements concerning this situation is true? Well, they're going to be connected across the battery, and they're going to be connected one end to end. That means there's only going to be one path, so the current through each wire is the same. We can eliminate number 1, and we can eliminate number 4. And provisionally, we'll eliminate number 5. So we get it down to 2 or 3. So they're identical except they're made from different materials. So the potential difference across them will be different because the resistivity will be different. So 3, the potential difference across the 2 wires is different, but the current through each wire is the same. V equals IR equals I rho L over A. So V is proportional to I times rho. Different materials have different rho, and in a series circuit, the current is the same. Okay, certain circuit contains a battery and resistor. An instrument to measure the current in the circuit, an ammeter, is connected in between the terminals of the battery and one of the resistor. The graph shows the current in the circuit as the voltage is increased. Which one of the following statements best describes the resistor in the circuit? Notice that the plot is linear between 0 and 25 volts. Well, if the plot is linear, this is obeying Ohm's law. So it obeys Ohm's law between 0 and 25 volts. So that's the correct answer. Thank you.